Good afternoon again. So this is my second lecture for my brand new physics course. And again, putting this completely on YouTube. I plan to do these lectures live for my class here at the school, but I thought that the way that I handle physics in the physics course, I think it could be benefit to some students for other schools. So again, we're in the Adler book. We're jumping around. So typically what I do is I pull apart. They mash all the physics content into about 5 chapters. All the electricity and magnetism and induction and transformers, and they mash it and compress it into 5 chapters, and then I spend my courses unraveling that. And so I present parts of chapters as I think they ought to be ordered. So apologies to Professor Carlton, Professor Adler, and Professor Barlick. I have my preferences. So we're proceeding. We're going to talk about physics as a science, where it started, where it came from, what is the scope of physics, what is the realm of physics, and then how does X-ray, the story of X-ray and the history of X-ray, fit into the story of physics? And we're literally second cousins to very renowned names like Faraday, um, Einstein, Bohr, Rutherford, Hertz. So not just Rankine, basically everyone who was a brilliant mind in the realm of physics around the turn of the century has a hand in defining the fundamental principles of X-ray science and how we understand how X-ray behaves. Not just Mr. Rankine. He wasn't working alone in the wilderness. He was. There was collaboration. There was sharing of ideas. There was discovery after discovery after discovery, and it kind of just spiraled into, well, quantum physics. So, all right, so let's get started. Our objectives for this lesson is um, the branches of science. So there are the fundamental natural sciences, physics, chemistry, biology, and then you have subsections of the geology, and then subsections of those, um, and more specialization as science grows as a body of knowledge and as a practice. Um, we keep discovering new things, and so we need more and more specializations, um, and so part of science is classifying what we discover. And so the first classification is what realm, or what is the scope of investigation? What is it we're trying to figure out? So that's where these branches of science come from, and the difference between physics and chemistry, and the difference between chemistry and biology. And yes, there are overlapping ideas, but they try to stay in their own lanes as far as the definitions of those words and those subject matters. So we are going to talk about matter and energy because that's the initial classification of stuff. Okay, stuff is a very handy word, but it's very vague, not very descriptive. And so we have to start with there's stuff, and then we have to figure, okay, well, what kind of stuff is it? And the first division of stuff is matter or energy. So, and then we further say, okay, about this matter, why is some of it behaving differently than others, right? And so we'll talk about structure of matter, and then we'll also talk about properties and characteristics of matter. We know that, for example, water is a molecule. Um, it's a combination of two elements, hydrogen and oxygen, in a certain arrangement, a certain molecular structure. And if you bundle lots of water molecules together, you get at room temperature and normal atmospheric pressure, you get a clear liquid. Okay, unless there's stuff in it, like pond water is not necessarily clear, but water without anything else added to it is a transparent liquid. So at room temperature, normal atmospheric pressure. Okay. But clay is not that at all. And then clay and other types of dirt or soil, or, if you're a farmer, it's soil. Um, there's a lot of variation, and we find that those things are mixtures. And then we can take dirt or rocks and we can melt them in a furnace and burn off all the lighter elements, and the heavier elements remain. That's called metallurgy. And we get purified metallic elements from processes like those. So, and with all of that, we find out that water and copper are not the same thing. They behave very, very differently. And that leads to, well, why do they behave very, very differently? And bang, now you have chemistry. Okay. And so that's where physics gave birth to chemistry, is this investigation of matter. And that is on the front end, that's like the grandfather to the discovery of X-ray, is figuring out what matter was and going, in really, really tiny pieces of matter, what does that look like? So, and then if we were to, so we did that investigation into matter. We also started an investigation into energy. Ben Franklin, Auguste Coulomb, Michael Faraday, other scientists were working with electricity, but then we also knew about fire. We knew about combustion. I think we invented the steam engine somewhere in the middle of the 1800s, and so we knew about. I think those are Boyle's laws for pressure relation to temperature relation to volume, and then that led rise to the piston and the steam turbine, the steam piston, and then the Industrial Revolution and that type of stuff. So, and then as we're doing that, we figure out more and more types of energy, okay? And we figure out the rules for energy in that process, okay? And then basic concepts of atomic theory, that's the immediate forefather to figuring out what X-rays are doing, is discoveries about the structure of atoms, those really, really small pieces of matter. Okay. Differentiate between radiations along the electromagnetic spectrum. I do have a separate lecture on electromagnetic radiation. But I think in talking about energies, I think I do just give a brief mention to the electromagnetic spectrum and the variety. It really is a variety of energies, a variety of frequencies, a variety of wavelengths, and we'll dive deeper into what those are, what those mean, and how those variations in energy, frequency, and wavelength change the behavior of the electromagnetic radiation into something harmless, like a radio wave, into something really stunning, like visible light, into something a little bit more dangerous, but also stunning, X-ray photons. Okay, and then we will go into briefly some properties of X-rays, and that'll be straight from Dr. Rankin's mouth. And I think there's an appendix at the end. That's his initial publication of the discovery of X-rays, is at the end of this Carleton and Adler book. And kudos to those professors, and Professor Bollock just recently added. Kudos to those three professors for seeing the value of preserving that part of the history, that you can actually go to the appendix of this book and read Rankin's original paper for yourself. So, all right. So here we go. This is Dr. Rankin. Okay, wink, wink. You might know him. He later went on to star in stage and screen and television. Very familiar face. Details of his discovery vary somewhat. Okay, which is curious, because he did publish a paper describing how he built the apparatus, how he set it up, the various experiments that he performed, and his conclusions about the behavior of these unknown, and that's why they're named X-rays. X was the unknown in algebra. That's an unknown variable. So X-rays is literally related to the X variable in algebra. So, um, so he made his unplanned discovery on November 8th, 1895, and it captivated him and stimulated his curiosity so much that he kept investigating for like the next 7-8 weeks. Okay. When he figured out that he was definitively on something, his wife happened to visit, and he said, "Oh, come here, check this out." And he actually had his wife put her hand in between the Crookes tube and a piece of photographic film and took the first hand X-ray. And that's famous. It's all over the internet, and I'm sure you've seen it 100 times. I think it's coming up in this slideshow. But that was like either end of week 1 or week 2 or somewhere around there. Okay, and so he worked with this from early November all the way up through Christmas, and then he, collected his notes, revised, and published a paper early in 1896. He published to a physics science journal that's circulating in Europe. But he was very particular that this was not to be this, whatever this was. This, when he saw his wife's hand, he said, "This is going to be important for medicine, and so I need to freely give it and share this information with the world. No patents, no copyright, no proprietary claim at all. This is too important for me to be selfish with this." So, yeah. Okay, but what the hell was he doing? Because it says he was working with cathode rays, and he was working with a Crookes tube. What's a Crookes tube? Who is Crookes? Okay. Why? It's an accidental discovery. So what was Rankin's original intention operating the Crookes tube? What was he trying to? Because he had an experiment that he was running, and then he figured out that the Crookes tube was doing something weird. Okay, so what experiment was he doing that totally went off the rails and took a left-hand turn, and now bang, we have X-rays? What the heck are cathode rays? What does any of this have to do with physics? What the hell is physics anyway? So these are all very good questions, and in my history telling and later on through the course, I'm going to answer all these questions. Okay, so let's get started on that. Oh, look, more questions. Why do objects fall back to Earth? These are some you might know. Yes, gravity, right. Good, you're familiar with it. Fantastic, you've heard of it. It's why you're sticking to the Earth right now and not flying off into space. That would be scary, wouldn't it? Okay. If they suddenly threw a switch and gravity turned off, everything that's on the surface that wasn't securely tacked down would just fly off on a straight line path into outer space. That would be surreal and, wow, just surreal and also traumatizing at the same time. Okay. Why does wood burn? Okay, so that's an energy thing. Why does it give off heat and light when it burns? Also an energy thing. Why do wool socks create static electricity in the winter? Well, not always, but if you have hardwood floors, not necessarily. They do keep your feet nice and toasty, but only wool socks on carpet create static electricity. Now, no one is, well, I was saying no one is fool enough to wear wool socks in the summertime, but there are some strange folks out there. Okay. But if you wear wool socks on a shag carpet in the summertime, you may get a little static electricity. every time. Unbelievable. Sorry about that. Yeah, so in the summertime, wool socks will not create as much or scant amount of static electricity. So something is changing between the indoor environment in the summertime versus the indoor environment in the wintertime that is allowing for static electricity to flourish more easily. So maybe chew on that a little bit. Why is a bowling ball heavier than the pencil? What? That's what? Well, it doesn't have to be, does it? Okay, you could have a really big pencil to, like Guinness Book of World Records type stuff. Okay, but I'm talking about the average pencil and the average bowling ball. Okay, they're made out of matter. Why is one, or even better, a chunk of lead and an equal sized chunk of brick? The lead is heavier. What's going on there? They're the same size. That's strange, isn't it? Yeah. And so those are differences in matter, and leads us into, okay, what is going on with the lead that a small amount of it weighs the same as some other materials that have much, much bigger volume. So why does the light turn on when I flip this switch? Yeah. And it's instantaneous, unless I mean, the UV lights, the old long tubes like you see in public buildings, like we have here at the X-ray school, there is a little bit of a flicker and a delay. It's about a 4-second delay or so. But most lights, it's instantaneous. You press the button or you flip the switch and it's on. You have light. And then you flip the switch again and it's off. What's going on there? How is it that flipping this switch on the wall is changing what's happening up in the light bulb? What is going on up in that light bulb? Okay. All really, really good questions, aren't they? Why does an X-ray machine produce X-rays? Well, the non-answer is because it's designed to do so. Okay. The better answer is basically the subject of this course. That's the end game. That's what we're getting to, is explaining the engineering that goes into both the circuitry and the design of the tube to show you how it's specifically built with the purpose to exploit certain rules of physics such that the conditions for making an X-ray photon are possible. Not only possible, but necessary. That is, it will happen when you have the right equipment engineered the right way and you create the necessary conditions. You will make X-ray. All right. So the subtitle of the book is An Art and a Science, and I love that. Radiography is an art. It is taking pictures. Okay, it just happens to be that those pictures are medically useful. Okay, but there is a subject matter, and there is a artist palette. There is a brightness and contrast that is preferred by the audience or radiologists. Okay, and the character and the details of the works of art that we produce, these still life photos of the inside of the human body. In order to be a good X-ray tech, you have to recognize that it is fundamentally, it's a picture. Pictures are art. Okay, you are expressing an idea through images. That's what any painting is expressing ideas through images. You're doing the same thing when you take an X-ray. Okay. But folded into the art and kind of as a support structure to that art is a well investigated, well known, and well exploited and engineered physical science and the technology that we utilize to take x-rays goes all the way back to not necessarily Newton, but definitely goes back to Michael Faraday. Okay. And so our first is physical science versus biological science. Okay. So physical science, physics is the first science. All other sciences, as my former physics professor said, are branches off of physics. Okay. So physics is the fundamental physical science. Chemistry is also a physical science. Geology is also a physical science. Okay, and I'll explain how those other two are branches of physics. Okay, so physics is about matter and energy. Okay, chemistry is about the behavior of very, very tiny fundamental quantities of matter and how those tiny quantities of matter, molecules and atoms, exchange energy. So basically, chemistry is the physics of atoms and molecules. Okay. Now, geology. Okay. Well, those are rocks, minerals, okay, ores, mixtures, compressed soils or sands, okay. All of those are made out of either elements or compounds. And so geology in a lot of ways is the chemistry of rocks. I'm going to upset a lot of geologists. And so if geology is the chemistry of rocks, then it is the physics of the molecules of the rocks. That's what geology really is. Okay. Biological science deals with living organisms, living matter. Okay. Anatomy and physiology is a subset of the greater field of biology. Medicine is, I wouldn't say it's a subset of anatomy and physiology. Medicine is it borrows heavily from, I would say, all the sciences in order to heal the sick. So it's an application of all the sciences: physics, anatomy, physiology, cellular biology, biochemistry, chemistry itself, X-ray science. We basically the gamut of every tool that we can grab to help heal the sick. We have grabbed it. So there's a little bit of everything in medicine, every bit of science in medicine. You encounter more physics in radiology than you do some of the other stuff. In pharmacy, you encounter more chemistry and more anatomy and physiology in nursing and surgery. Okay. But you are relying on lots of information from lots of different sciences in the practice of medicine. All right. So I can't play a nested video inside a recorded video, but this is just a clip of, I think it's Michio Kaku, telling us about what the heck is physics. So he answers it better than I do. I might be able to link to that on the YouTube channel in the comments section and direct you to this video. And I think I've got some others coming up. So if you're seeing this live in my class, then I'll play this clip. But all right. So matter and energy. Physics is the attempt to understand and classify the known universe, basically everything. That's, again, every physicist will tell you that every other branch of science is a branch of physics. Okay. Because that's all there is matter and energy. Things are either matter, therefore they have mass and occupy space. They are what we call objects. Okay. Or they are energy. Energy is manifest as forces that do work, and work has a special, it's not like, okay, I'm clocking in and now I'm making t-shirts for the next 8 hours, or I'm making tacos at Taco Bell. No, work means a force applied across the distance. That's the definition of work to a physicist in classical mechanics. So energy is the manifestation of that force that we see either pushing or pulling on objects, or manifesting in other ways. Okay. But the first definition is force used to do work. Now, what force does a fire apply? Well, that's when the definition breaks down a little bit. This is the definition of energy from a mechanical standpoint, so to speak. You're applying a force to, say, a piston, and the piston moves. It compresses, and the plunger compresses into the chamber. Well, a certain force has to be applied to move the plunger in and out of the piston. And so we call that as the energy being consumed by the piston. Okay. And so this definition of energy fits best with a mechanical understanding of energy. But as we see with some of the varieties of energy, it's really hard to fit this definition of energy to like X-ray photons or electricity. Well, electricity fits a little bit better when you take electricity and put it into a motor. You create rotational mechanical energy, and so now you do understand it again. So, all right. So, Isaac Newton, that's the guy with the long hair, not the other one wearing the Bulls jersey, if you didn't know. Isaac Newton is the Michael Jordan of physics. he's the first, and arguably I say he's the best. Okay. I think he was 22 or 23 years old when he figured out, he invented a new branch of mathematics with this book, and he had to do that, he explains, so he could figure out the instantaneous rate of acceleration of the moon. Yeah, he solved the math equation for the orbit of the moon. That was the point of this book. It's like, I have a copy of it translated because he wrote it in 1687, so he was using Old English. I have it translated to modern English. This book is 600 pages long, and I can get through about 3 or 4 pages at a time. That's how cognitively intensive this book is. This man wrote this when he was 22, 23. Figured out the mathematical formula for the orbit of the moon and invented a new method of mathematics to do it. Holy crap. I wish I was that smart. Okay. So Newton had an immediate impact. Basically, this book started the mathematical deduction and the mathematical figuring out of how does nature behave. Okay. Once Newton got onto the idea that it wasn't God, we need something more specific than God was holding the moon up and making it spin around the earth. We needed mathematical rigor. We needed provable rules, measurable calculations, okay, and predictions. So we needed to write an equation that explains the motion of the moon, and then if you enter in a future time, right, and punch through the equation, you can predict the position of the moon like 6 years down the road. And that's literally the proofs. That was the challenge that he called out the rest of his scholars, folks that he considered his equal. He's like, go ahead, get your telescopes out, and to use the equation. Here's near the end of the book, here's my solution. This is on this day, this night, this time. The moon's going to be in this position from City of London. And one of his good friends was Edmund Halley, Halley's Comet. Halley definitely put that to the test. He definitely had his telescope out. And lo and behold, yeah. And not only that, but it was repeatable. So Halley applied it to just random dates. He took the same equation. Newton had given a specific date, like 6 years in the future or something like that. Halley took the same equation and just started plugging in random dates and got his telescope out on those dates and never missed. He just didn't even look at where the moon was, pointed at the telescope and then looked at his telescope and he was looking at the moon. In 1687. Okay. Nowadays, it's like a big deal. We got a computer. We got a telescope built on the hill outside of every major city. You punch in a bunch of numbers and it pivots there for you. Big deal. Oh, where'd they get the computation from inside the software? Where's that? What's the source code for that? Who's the originator of that computation? Okay. That's how big an effect this was. Telescopes, the university telescopes to this day, the astronomy telescopes that you have to be a doctorate of astronomy in order to be even considered, and you have to have a fully funded grant research project in order to rent time on the telescope. The guidance for that telescope is Newton's formulas. So classical mechanics plus relativity, Einstein, GPS and all that. Yeah, there is relativity has been applied, but yeah, at the base of it is the formulas that he conceived in this book. Yeah. All right. So revolutionary. Next 400 years, everyone was like, "Oh my God, Newton said this," and so then and it's basically 1687 was the real start of the Industrial Revolution, because without Newton's book, we wouldn't figure out pulleys and levers and pistons and engines and locomotives and things of that nature. All of that stuff was engineered with classical mechanics in mind, with the formulas that Newton published in this book describing. All he was trying to do is say, look, silly, the orbit of the moon is mathematically predictable. It's a regular orbit, and you can write a math equation for it. In fact, this is what I'm going to do. I'm going to write that math equation. In his journey to do that, he theorized and later proved that gravity was the force. Right? And they knew about gravity. Gravity was the force, but gravity behaved according to mathematics. Okay? And because gravity behaved according to mathematics, that yielded mechanical forces and then engines, pulleys, simple machines, all that stuff. So the Industrial Revolution starts with this book with Isaac Newton. Okay? And so we just keep going and we just keep everything's Newtonian system. Let's apply this book to this problem that we have to solve. And let's see if we can build some kind of machine that capitalizes on these forces and this acceleration. And bang, you build a locomotive, right? You build the steam engine. You build steamboats, right? You have this huge boiler in the middle of a boat, a ship, and you don't need sails anymore because you have this big paddle wheel in the back, and it just propels the boat forward. Crazy. Self-propelled boat. You don't need the power of the wind. Okay? You don't need oars. The steam engine is doing the rowing for us. So, yeah. So physicists, they just kept going, and eventually, okay, well, wait a minute. We're using wood, and we're using some metal, and we know how to forge iron and steel, and we're making all these wonderful things, but a lot of this stuff is different from each other. And to be fair, alchemy was the precursor to chemistry. Alchemy was, I think it started with the Romans, actually, maybe even the Greeks. the classifications of different types of materials. Okay, metallurgy was known all the way back into the Bronze Age. The Bronze Age started metallurgy, and then we learned how to isolate and separate certain metals, learned how to make alloys. Bronze plus tin is brass. Yeah. So bronze plus tin is brass, and brass is harder than bronze. And so, yeah, we knew a little bit about elements, but what's the smallest piece of matter? What is the smallest? Why is brass behaving like brass and water behaving like water? And what are these things really made out of? How small can you divide water and it still acts like water? Is there a lower limit? Can you get the smallest piece of water, so to speak? And then if you try to break that apart, then it's no longer water. Is that limit a thing? And so that was John Dalton, which was one of the three individuals previously, right there with Newton, and the other one was Louis Pasteur. Newton, Pasteur, John Dalton, chemistry, germ theory, and physics. Okay. Chunk of stone. Say you had a stone. Okay. I don't know, shale, whatever. It's something you can split. Okay. You split it in half. Okay. So do both halves still act like the same stone? I mean, they weigh less. There's less mass. There's about half the mass, right? Which is the quantity of stuff, the quantity of the stone. But it still basically acts like, so it's, say it's a slab of slate. It's still, both pieces still act like slate. How long can you keep doing that before it's like, okay, because it could turn into sand eventually. And then sand is clearly not slate. Okay. And then the sand has grains. Can you smash the grains into a powder? And then if you had a knife small enough, can you slice up the flecks of powder? Okay. How far down can you keep taking smaller and smaller pieces of the stone, and then it changes its behavior? It no longer behaves as if it's a stone. Okay. Is there a lower limit to that, to the where you get characteristic behavior, but if you take a small enough piece, you lose that? It doesn't behave like that anymore. So that is, what are the components of matter that's making different things behave differently? Stone and a bucket of water are very different things. Okay, water is liquid, stone is solid. What does that even mean, liquid and solid? And then there's gases too. We're breathing air right now, that's gas. Okay, and we're told in science we pretty much accept those are states of matter. What does that mean to be in a state of matter? Why is liquids? Why are there liquids? Why are some things liquids and other things solids and other things gases? Why does it do like that? Why is it so different and so variable? Right? And that's the fundamental question of chemistry. That's how chemistry starts, is this discussion right here. Okay. All right. And so that leads to John Dalton, the father of chemistry, and Mr. Mendeleev, Russian chemist, that proposes the periodic table, and away we go. Okay, so John Dalton kicks it off and says that there's atoms and there's indivisible pieces, and if you purify those atoms in all of the same type, that's called an element. And so there are pure forms of things, and then there are combinations of elements. Those are molecules. And then there's mixtures where it's a random assortment of different molecules and different elements, like most stones are. Most stones are just mixtures that are in the solid state. Okay, if it was in the liquid state mixture, that would be lava. So, um, yeah, and so everyone starts to, Dalton proposes that there's atoms and there's fundamental elements, and that is there's um, different, the atoms of oxygen are different than the atoms of carbon that are different than, and we don't even know all the types of the elements. We know some. We've given names to some, like hydrogen and oxygen and carbon. They figure things out, and then the race is on in the early 1800s through the middle 1800s, and that's where this very fashionable gentleman comes in, Sir William Crookes. Man, look at what we did to men. Look at how pretty that facial hair is. Look at that. That needs to come back. Look. Oh my God. I could just stare at this dude all day. Okay. Just, that must have took like a good 40 minutes to, comb that mustache out and apply, half a pint of wax and then comb the beard out and get it all picked and fluffed. And, yeah. And then put on a fresh shirt and a tie and, yeah. Tuxedo, it looks like. That might be just an old suit. That might be the style. So, this is Sir William Crookes, and he was consumed with, on the heels of Dalton and others, he wanted to get his name in this, as many of the folks right after Dalton. It was like, let's discover some elements. Okay, and so they started doing everything. They started, taking samples out in nature, go to all different corners of the planet. Hey, your dirt is orange. Let me have a little bucket of that, a little pouch of that, and I'll take that home and I will filter it and then put it in an acid bath, and then I'll put it in distilled water, and then I'll filter it again, and then I'll submerge it in oil, and I'll try to separate it into its components, because some of the contents of this red soil is going to want to dissolve in the acid. Other contents is going to want to dissolve in the oil, and other contents is going to prefer the water. And they just started trying different ways to basically take apart soil samples and ore samples and get to a pure element. So where they had something, they didn't know what it was, but it was basically a mound of powder that they had extracted from this mixture. And the idea is this mound of powder is either an element or a compound. It's either a naturally occurring salt or it's a purified element. And then I'm going to begin testing this sample and see if I can come up with some unique properties. And if I find, and then I'm going to consult my colleagues' journals, where everyone's publishing, and see if I can find some unique properties that have not been observed before. And then I might have a new element. Okay. And so one of the ways they were doing this was spectral analysis. Now, you might have seen this. I don't know if they still do this in a high school science class. They did it for me. Is the Bunsen burner test. So if you get certain metals, powders, and you burn them in a propane flame, which is blue, it changes the color of the flame as you oxidize the metal. So I think magnesium is like yellow, strontium is red, and this is also where the color of fireworks comes from, guys, is the spectral test. And so they used to burn part of the sample over an open flame, okay? But then they did have some laboratory fires and some carelessness. It turns out, in fact, some of the metals on the very far left of the periodic table actually spontaneously combust in their pure form as soon as they come in contact with oxygen in the air. Sodium is like that. Purified sodium will catch fire in the air by pulling oxygen from the air. It will catch fire in a humid room because it will steal the oxygen from water in order to create sodium hydroxide. Okay. If you throw a brick of purified sodium into a swimming pool, you'll get an explosion about half a second later from the violent exothermic reaction. Okay. All right, so William Crookes is on this quest to make make himself famous, make himself a proper scientist, and discover an element. And he does so by um, a new alternative to spectral analysis, and that is cathode ray bombardment. And he actually invents his own Crookes tube, uh, which was an electrical apparatus that would broadcast cathode rays. Okay. Now they didn't know what cathode rays were. They just know that they were related to electricity and they were invisible. Okay. And so the Crookes tube was an electrical device, and it seemed to give off cathode rays, and the cathode rays would produce the same spectral analysis colors without combusting your sample. And so your sample might glow with the same color you would get from the flame test, but you wouldn't destroy your sample. So the Crookes tube spectral analysis was actually safer and less costly because you only had a certain amount of this unknown sample before you had to go and get more dirt and try to extract more of this unknown element, if it is an unknown element. Okay. And so there's a time and a labor cost involved with destroying your unknown. And so a lot of physicists were converting to this alternate form of spectral analysis so they could preserve the sample for other tests. Okay. Crookes actually witnessed X-rays. He actually saw the same thing Rankin saw, but it didn't like the curiosity. He was consumed with. He was really close. He discovered thallium from it, and he mentioned in his notes later on. He mentioned in his notes that he saw that certain things glowed. Not the sample that he was aiming his Crookes tube at. Other samples that he had on the other side of the room, which were known metal salts, they were glowing. And they figured this out after he died. Someone read his personal notes and journals, his scientific notebooks. But he never gave it the name X-ray. There was no connection made till it was only here in the modern era do we recognize that what he published in his notebook was X-ray. So, yeah. A unipolar tube. So those of you who don't know, you should know. This is Nikola Tesla, perhaps the smartest individual ever lived. Okay, even Einstein, when asked famously, "What's it like to be the smartest person who ever lived?" he said, "I don't know. You would have to go ask Nikola Tesla." So, Nikola Tesla was he was more than a scientist. He was kind of out there. He was kind of eccentric. He was kind of little touch of the crazy. Doesn't hurt sometimes. He just imagined things that the bounds of his imagination were beyond any one of his peers or his colleagues. He dreamed up so much stuff that he didn't really have a mind for the mathematics side. He just this is and he imagined it and then he made it so, and sure enough it worked. Okay. It was just off the charts genius. Okay. And unfortunately, because he was a little bit of a little strange, he also didn't have very much safety consciousness. Okay. And so in fact his Tesla coil it's a lightning machine. It's a if it's ramped up to too big of a magnitude, yeah, it creates lightning bolts that could stop your heart. So yeah, not a very good mind for safety, and also working at a time where a lot of the materials they were working with, a lot of the things they were investigating and experimenting with, yeah, fires broke out all the time. Okay. And so he had so many research projects and so much stuff. Now, the FBI confiscated his later writings, right, after he worked with Westinghouse. Um, but his early work was lost to a fire in Manhattan in the spring of 1895. Okay, he wrote to William Rankin later upon hearing about X-rays. He said, "Oh yeah, I figured that out. I called those shadowgraphs." Okay, and he used a unipolar tube to create his shadowgraphs. Okay, but all his work, his diagrams, and his journals about these shadowgraphs burned in a fire in spring of 1895, just about 6 months before Rankin uh, discovered X-ray. So we almost read about Nikola Tesla as the father of X-ray. All right, or Mr. Crooks. Okay, now this, I don't like this picture of Rankin. I do need to swap it out. This is Rankin as an old man near the end of his life. Um, all right, so same slide. Details vary somewhat. Now we're back. Now we know a little bit more about what he was doing. He was also chasing his own periodic table of the elements. Okay, and I think ironically, posthumously, they did name a new element after him. I think there is a rankinium on there somewhere. Okay, I'll have to look that up and confirm that to be sure. Hang on just a second. No, I was mistaken. It was I was thinking of either Einstein or Rutherfordium. That's who it was. Yeah. So yeah, Rankin. There is no Rankinium. I made that up. God bless. Okay. I thought for sure. Yeah, it's funny how the brain works. Thought for sure there was an element named after Rankin. Okay, but that was what Dr. Rankin was actually chasing. He was doing a Crookes tube experiment, spectral analysis. He was trying to discover a new element. Okay, but as the best thing in science is incidental finding, and um, incidental finding is how we discovered X-ray. Okay, and so um, whenever you conduct an experiment, and as a good scientist, just watch everything because something weird's going to happen. One of these days, something weird's going to happen. You'll be like, oh, that's odd. I wonder if I can make that do that again, right? And then you do. It's repeatable. Okay, well, that's scientific discovery right there. And so that's what Rankin. That was the first thing is like, oh, that's strange. That's glowing. Oh, is that really glowing or my eyes? Because he had the room lights dimmed so he could see the cathode rays. He's like, is that really right? And so, he made absolutely sure, right? And then he cut the power to the Crookes tube, and the glow stopped. He's like, okay. Turned the Crookes tube back on and looked over, and the glow came back. Held up a piece of paper between the Crookes tube and the glow. It's still glowing. Okay, well, I got a piece of sheet metal here somewhere. Grabbed a piece of sheet metal, held it up. The glow stops. So something is coming out of the Crookes tube and interacting with that plate. Paper is not a sufficient barrier to stop it, but sheet metal is. Strange. What is that plating? And then, turn all the lights on. That's barium platinum cyanide. Huh. Wonder if that has anything to do with it. Okay. And so he started testing other materials if he had other uh, compounds. Well, this one glows green. That one glows purple. That was actually Thomas Edison that did that experiment. But anyway, um, but yeah, he just kept working with it. Okay, doesn't bend around corners. No, it seems to travel in a straight line. This kind of stuff seems to be able to penetrate some materials, but other materials not so much. Metals seem to impede it fairly efficiently, but um, wood, paper, it still glows on the other side of the wood, on the other side of the paper. So he just kept practicing with it. He just kept trying to figure out what it was and started taking notes on the various, he tried different ideas, started taking notes and such. And 7 weeks later, published a paper. Okay. December 22nd. So that was, oh God, that wasn't week 2 or week 3. That was November 8th. So 3, that's like week 5. Week 5, week 6. Okay. So the properties of X-rays that we know today, his investigation was so thorough that we really didn't figure out much new about X-ray for a very long time. Okay. It is almost a comprehensive understanding of the behavior of X-ray photons. Okay. Effect photographic film. Okay. That was week 5 or 6, December 22nd. Okay. That's the first radiograph right there. That's his wife's hand. Okay. And so the usual joke goes like this. Doctor's dictation, December 22nd, 1895. Subject presents with a PA view of the left hand. Artifact is present at the fourth finger. I have to write up the technologist for failure to remove a wedding ring. Looks like a portion of the fifth phalanges, both distal, intermediate, and proximal, are clipped from the view, as well as the first digit. Okay, the second and third digit, the pip and dip joints are not open. Fingers are flexed. Looks like through all of the digits 2, 3, and 4. Open metacarpal phalangeal joint spaces, underpenetrated at the ring finger, finger number 4. Study lacks oblique and lateral views. Recommend repeat. No conclusions can be drawn from this limited study. End dictation. All right. How did I do? Yeah, that's exactly how they talk. Okay. So, use of X-rays. Physicians readily embraced this new technology, immediately put it to use. Okay. So, Rankin saw the worth, how it will fundamentally change medicine, and it absolutely did. It was so powerful a tool that he's like, no, you doctors have to find a physicist, build these things, put them in your doctor's offices and in your hospitals, and you can see the bones with these machines. Okay. And bang, we got a new branch of medicine. Radiography was born. Okay. And the physicians, so it hit the physics publications, the physics journals. It was translated into English and other languages, sent all over the world. And then it was shared with the medical journals. And then the doctors discovered it. And then bang, it took off. I think it was February 1896. The first x-ray in America was taken. A young boy out in Boston slipped and fell on the ice and x-rayed his wrist. So literally, I think Rankin published in January, so 1 month later, we had built an x-ray machine outside of Boston at Dartmouth College. So physicians readily embraced the new technology. Early cathode ray tubes and generators were inefficient. Okay, we didn't understand electrical engineering. This is more just, okay, you hook up this simple circuit and you push a little voltage through it by use of, those are actually early forms of batteries. Those are called, I think those are called Leyden jars. Okay. Those are early forms of batteries. over there on the cabinet, and he's got lead wires running from. There's two of them. I think there's probably a wire in between them. So that's what's creating the electricity, the current, is those Leyden jars. They're filled with, I think they're filled with an acid. They're like nested jars, and I think there's an electrode in the top of the jar lid. There's like a copper rod that you dip down in acid, and then the inside of the jar is coated with stainless steel or aluminum or something. And so you get a chemical oxidation reaction happening between the copper rod and it's like cathode anode. Okay, and so you get a crude battery, right? You string these batteries together like they've done in series, and you can get a voltage. Is it a kilovoltage? No, this isn't engineering. This is, yeah. So early X-ray beams were very weak, inefficient, and you can see that it's a glass bulb in front of that doctor. There is no shielding or shrouding either. Okay. There's also live electricity going through that thing. Okay. And so there's alligator clips like jumper cables on a car connecting the wires to the ends of the X-ray tube, to the ends of the Crookes tube. Okay. And then you have these crude, basically chemistry lab armatures holding up the circuit. So, yeah. Okay. This famously is Thomas Edison with his assistant Clarence Daly, and that is the prototype fluoroscope, ladies and gentlemen. The tall box is the generator mechanism, and then inside the small box that the hand is resting on, there is a X-ray tube that is working right now, making X-rays inside that box. And then Edison is holding the fluoroscope, which was literally just a cardboard pyramid with a broomstick handle attached to the bottom. He painted the bottom of the pyramid with calcium tungstate, and Edison's contribution is the invention of the fluoroscope, but also he figured out the other heavy metal salts that also produced visible light. And better than barium platinum cyanide was the calcium tungstate that Edison used for his phosphor in his fluoroscopes. Okay, we'll hear about Clarence Daly in radiation protection and radiobiology because he, with his experiments on the fluoroscope in combination with Edison, he ended up losing 9 of his 10 fingers and then succumbing to radiation illness, tumors, burns, basically an early form of acute radiation syndrome. Yeah. All right. So then the engineers and the physicists got involved. 1903, probably the most significant development in X-ray science was instead of a cold cathode, let's do a hot cathode filament, and let's make it out of tungsten wire. Okay, and the only person that could have done that was Dr. Coolidge from MIT. Um, Graduated with a degree in metallurgy and immediately went to General Electric. Worked underneath Thomas Edison for a brief period of time. Eventually went on to become the boss of GE. But he invented tungsten wire. Tungsten is not malleable. Okay, so it's a metal. It has a high heat capacity. It can conduct electricity fairly well. Okay, but like steel, you can heat it up to near melting and stretch it into wire. Okay, tungsten, if you try to do that, it's brittle. It'll actually break apart like glass. So it's not malleable. It's not shapeable. Okay. So what he actually had to do is take those bricks of tungsten and shave them into powder and then make a mold that was filament wire sized and sprinkle the tungsten powder into the filament mold, the wire mold, and then heat it up to melting and let it cool back down. And it formed the powder melted into a liquid, formed the shape of the mold, and then when it cooled back down, that's how you have tungsten filament wire. Okay. Until that time, they couldn't figure out how to make certain metals into filaments. So that was a revolution in metallurgy. Um, Tungsten filaments that Coolidge invented immediately replaced the bamboo, carbonized bamboo filaments that Edison was using in his conventional light bulbs. And so Coolidge did this to make the light bulb more efficient, but then he figured out that the Crookes tube could be made more efficient too through the same process. And it was called the hot cathode filament. So, and this is a electrical schematic of Crookes's new tube. He had a water-cooled anode too. You would hook this up to a faucet and then run the other hose to a sink drain, and you could keep your anode cold. Okay, so you wouldn't burn your tube up. So two brilliant engineering redesigns that made Coolidge tubes a little bit more hardy and durable and capable of sustaining higher currents of electricity and better X-ray beams. So, yeah, Coolidge is, and I think I've got a coming up. Yeah, this is actually him. I'm actually probably won't play well on the record later. I'm just going to skip it. But I do have this on my channel. You can look that up. That's William Coolidge. That's an actor there. That's not Rankin. But that is his lab. They still have his lab preserved in Germany. But William Coolidge takes over the narration for this and explains how the X-ray tube works. Pretty neat video. So. All right, and then Madison Avenue took over, marketing took over. I actually have a can of X-ray stove polish in my office, gifted to me by a previous student. If you'd like to come see it, it's just graphite. It is not radioactive. Okay. X-ray headache tablets. Yeah, there's nothing X-ray about those headache tablets. It's just aspirin. Okay. Disease preventative prophylactic. Yeah, no thanks. I'll pass. Okay. And then an X-ray golf ball. Okay. I don't know how a golf ball has anything to do with X-ray, but you'll buy it because I slapped the name X-ray on it, and it's the early 1900s, and X-ray is the latest thing. Okay. And so, yeah, acute radiodermatitis, where the skin, you basically started getting like a sunburn, but it's a radiation burn from using the X-ray machine too much. But we started to figure out, hey, this stuff is dangerous, and we need to shield and such. Okay. But let's keep, we're going to shroud the thing in a metal box and only have one exit to the metal box. But let's keep experimenting and playing with it and figuring out, let's take it to the shoe stores and fit shoes with it. What? Oh, let's cure headaches with it. Yeah, this is an actual ad from a paper. Okay. Kohler's Cure. You could basically, you get 8 doses for 25 cents. Okay. Mailed to any address in the United States on receipt of price. So he basically shipped you an X-ray machine, and you could plug it in or crank it up if it was a hand crank dynamo, and dose yourself to your heart's content, and it would cure your headache. See those are the demons inside your head that are creating the headache, and you have to kill them. It's quick, it's safe, it's sure. Well, not really, but okay. Okay, and yeah, this is actually Some of your grandparents might actually remember these machines. They used these. This is a fluoroscope. You stick your foot in the bottom, right, on the right, and you, but also your family, because see the guest viewports can look and see X-ray blasting through your foot with your new shoe on, and look, and you can see the fit of your shoe through a fluoroscope. Okay, they used these all the way up to the 1950s, folks. Okay, come on, glaucoma for the whole family. You know, have your wife come down, have your kids come down. They can get glaucoma. Get them started early on glaucoma. Come down and stare X-ray radiation straight into the eyeballs. All right. So that is basically how we got to X-ray science from Isaac Newton. It was Dalton said that there's atoms, and these atoms, pure forms, those are elements. They have names, and some of them are unknown. And everyone started discovering things. And William Crookes invented the Crookes tube to create a safer way to discover elements and some of their properties. And then Rankine was using a Crookes tube to chase his own element discovery. And bang, now we have X-ray. Okay. All right, so we've already been through math and algebra review. We're talking about the history of X-ray right now. Then we're going to go basically jump into science, concepts, formulas, notations, things of that nature. And we're just going to start with this is how we measure things, SI system, centimeters, meters, milligray, sieverts, those types of things. Conversions from different magnitudes of units, a kilometer. How do you convert that to meters? Well, you multiply by 1,000, so on and so forth. Okay. Newton's laws of motion, because not because it's on the registry, but because you're familiar with it, and it sets up how the electron responds to forces, because the electron is a particle in our understanding. Okay. Yes, if you go on the internet, they'll tell you the electron's a wave. Okay, not for passing the registry. It's not. It's a particle all the way down. It's a particle. Okay. Newton's laws of motion. So explaining the motion of objects when forces are applied to them, that's going to come in handy when we start applying forces to the electron. Okay. Thermodynamics and heat transfer. Basically, it's the science of how energy changes and converts forms. Okay. And there are certain rules about energy exchange. Well, we create a lot of heat in the X-ray tube, and so we need to know just a little bit about thermodynamics. Okay. And then the second rule of thermodynamics explains why scatter radiation happens. Okay. Atomic theory and the Bohr model. So the X-ray is made on the atomic level, and the X-ray interacts with atoms on the atomic level. And so we need to understand the basic components of atoms. Now, there is a modern Schrodinger model that really doesn't help us explain X-ray science any better. The Bohr model is sufficient. There are some flaws in the Bohr model. It's not perfect. The Schrodinger model is better. But the flaws that the Bohr model has, those are acceptable flaws for adequately explaining X-ray phenomenon. Okay. Electromagnetic radiation. Of course, X-rays are electromagnetic radiation. So we have to talk about what is. I've been saying photon like you know what that is, but do you really know what a photon is? I will show you what a photon is when we get to that chapter. Okay. Electrostatics, electricity and magnetism, circuit components. So basically, I turn you into like amateur electrical engineers at this component, because we're building from how do charges behave, electrostatics, to how do we get charges to move around, how are magnetic fields created, how do we create machines that exploit electricity. That's your circuit components. And circuit components, and then what are the rules to building a circuit? What are some of the rules involved once you have a circuit? And what are the symbols we use to draw pictures of these circuits? Okay, and those are straight electrical engineer symbols. Those are schematic symbols. Okay, so you will speak electrical engineer. Okay, you will be able to read some schematics. It's not a full set. It's enough that you understand the X-ray circuit, the circuit for a simple X-ray machine. Okay. Then we'll talk about voltage waveforms. So voltage is a property of electricity, and you can vary how you send it, AC or DC. Okay. The X-ray tube itself, we'll go into the piece parts of it, and there's some engineered components that work well, and then there's some engineered flaws to the X-ray tube, and we'll discuss those. Tube rating charts, heat damage. How do you destroy an X-ray tube? How do you abuse it? How do you set it up wrong? Can you overload an X-ray tube? Can you melt the filament? Can you put a melt hole into the anode wheel? Yes, you can do all of those if you don't know what the heck you're doing and you override safety protocols. Okay. And then finally, falling load generators, which are not as common anymore. I would think they'd still be common, but I don't know. I'd have to really pay attention to the modern equipment, but I don't think we're using much in the way of falling load generators anymore. But I'm still going to explain it to you because it is a thing out there.